So we were talking last time about substitution reactions. We were talking about various potential mechanisms for this reaction in which we are breaking a carbon iodide bond and replacing it with a new carbon-carbon sigma bond. And because we're substituting one group for another, we call this a substitution reaction. We talked about how this was thermodynamically favorable because the carbon-carbon sigma bond is stronger than the carbon iodide bond that we broke. And we considered a few different mechanistic possibilities. One was the sort of yuck option where we considered let's first make the new carbon-carbon sigma bond, then break afterwards the carbon iodide sigma bond. And the reason we didn't like this is because there was going to be an intermediate in between those two where we had carbon bonded to 5 things. And we talked about how carbon is too small to make strong bonds with 5 different things. Our second option, which we liked a bit better, was that we're going to break the carbon iodide sigma bond first. That will lead us to a carbocationic intermediate. And then at that point, the nucleophile could attack, and then we would make the new carbon-carbon sigma bond. And we liked that better. The structure of the carbocationic intermediate maybe made us a little bit uncomfortable because it was a positively charged carbon, but at least we weren't breaking the octet rule. We said that the rate determining step for this reaction would actually be the step where iodide takes its electrons and leaves to give you the carbocationic intermediate. We said that the transition state for this reaction was really high in energy because you're breaking a bond and is the rate determining step for the reaction. And if you were to draw that transition state, probably it would look something like this, where the iodide bond, carbon iodide bond, is lengthening. Some partial positive charge is building up on the carbon. We'll use the double dagger to indicate that this is a transition state. And we said that though it's weird, this can happen whenever kinetic energy from other molecules is transferred to a methyl halide in a way that excites the vibration of the carbon iodide bond to the point where iodide breaks off and leaves. And we said that this first step would be endothermic because you're breaking a bond. And then in a second step, after we make that carbocationic intermediate, then a nucleophile could attack to give you the desired products. Incidentally, if arrow pushing in this way is new, here's how you use the arrows. You have them start either with lone pairs or with electrons in a bond, and then the arrow must either end at a nucleus or in the space between 2 nuclei. So in this case, the arrow ends with iodide, communicating the fact that iodide takes those electrons and leaves. And then in the second step, we have lone pair electrons on cyanide attacking the positively charged carbon. You can actually understand this step as a HOMO-LUMO interaction where lone pairs on the cyanide attack the empty p orbital, that is the LUMO of the carbocation. We said that, let's see, the rate of this reaction depended only on the concentration of methyl iodide. In other words, the reaction was first order in methyl iodide, but 0 order in nucleophile, because the nucleophile is not involved in the rate determining step. We said that this reaction is therefore unimolecular. That's just another way of saying that there's only one concentration term in the rate law. And then overall, you can call this reaction mechanism SN1. 1 is for unimolecular, N is for the nucleophile, nucleophilic, and S is for substitution, which is what's happening in this reaction. Nucleophilic unimolecular substitution. One potential issue that's confusing to some people that I want to address now is that the 1 does not refer to the number of steps in the reaction. This SN1 reaction mechanism is a two-step reaction. You go from starting materials through a high-energy transition state to a carbocationic intermediate and then to products. This is transition state 1. It is the rate determining step. And so the 1 doesn't refer to the 2 steps or the number of steps. It simply refers to the number of molecules involved in that rate determining step. All right? Any questions you want to ask to review that? Go ahead.
Will a two-step mechanism always be unimolecular or an SN1? And then will ones always be SN2 or there exceptions?
Good question. Will a unimolecular reaction always be SN1 and no, there are other reactions that feature other kinds of bond breaking that might be unimolecular as well. So that's just sort of a general feature of reactions that only involve one molecule in the rate determining step.
Like a two-step mechanism that would be like this is SN2.
So could you think of a two-step reaction that might have a two concentration terms in the rate determining step? Yes, I think so. I mean, there are a lot of reactions in organic chemistry that are multiple steps, and some of those steps do involve 2 molecules. So without pointing out a specific example, I would say yeah. So it's good to think of unimolecular or bimolecular as having nothing to do with the number of steps. Yeah. Others? Good. Okay. All right. Then let's talk about our third option, which we thought was reasonable too, and that is we're going to do both at the same time. And in this case, we said if we were to actually draw what we were to draw what the transition state for the reaction where we were making the new carbon-carbon bond at the same time as we're breaking the carbon iodide bond, it would look something like this: a lengthened carbon iodide bond that's partially broken, partial negative charge on the iodide to reflect that it's not totally broken yet. Same thing on the other side, the nucleophile coming in, partial negative charge on the nucleophile to indicate that the bond is forming but is not completely formed yet. We'll use the double dagger thing to indicate that this is a transition state. An interesting feature of this transition state that we drew last time is the idea that the group that is leaving, the bond that we're breaking, is on the opposite side of our transition state as the bond that we're forming. And the reason we've drawn it that way is because this arrangement keeps the 2 negatively charged areas of our transition state as far apart as possible. This minimizes electron-electron repulsion. There's another reason for it too, though, and to do this we should consider what happens as the nucleophile starts to attack. You can think of this mechanism where we form the new carbon-carbon sigma bond at the same time as we break the carbon iodide bond. As a HOMO-LUMO interaction, you've got lone pairs on the nucleophile. As the HOMO, you have the carbon iodide sigma star as the LUMO. If we were to draw where that sigma star is, we would have small lobes facing the node in between the 2 nuclei, a large lobe on carbon and another large lobe on iodide. I'm going to use color to just represent wave function sign to show you the places where that changes. The nucleophile dumps its electron density into the sigma star. It does so at carbon, and the place where the LUMO is mostly at carbon is on the backside. That is 180 degrees away from the carbon iodide bond. And when we dump electron density into the sigma star, we break the carbon iodide bond and iodide leaves. So this is how we would draw the mechanism for the reaction where we make the new sigma bond and break the old sigma bond at the same time. Notice that when I have both of these arrows in the same, drawn on the same structure, I communicate that I'm doing both of these things in the same step. A question I often get at this stage is why, if the LUMO is on both the iodide and on the carbon, why does the nucleophile attack on the carbon? And the reason for that is that that's the best option in terms of the products that you get. So we've drawn the products of this reaction. If we attack at the carbon, we get a new pretty stable carbon bond, and then we get I-. So the bond here is stable, and the negatively charged molecule is stable too. The reason you can tell it's stable is because it is the conjugate acid of, or conjugate base of HI, which has a pKa of like -11. In contrast, if you were to attack from lone pairs on this carbon to the iodide, you would make some kind of weird carbon iodide bond. This molecule is so reactive I've never actually even heard of it, though you can use its relative, which is called cyanogen bromide, to break apart other molecules. So not only is this bond weak, but the group that would have the negative charge afterwards is the conjugate base of methane, which has the pKa of 50. So this other option is crazy unstable, and so it doesn't happen. All right. When in the mechanism where we're going to form both bonds at the same time, the nucleophile comes in from the backside because that keeps the negatively charged things in the transition state as far apart as possible, also because that's where the LUMO is. All right? Questions you want to ask about that? About that mechanism? Go ahead, Curtis.
Are there cases when the pKa's are closer together on those two pKa's of HI versus methane?
Oh, so are there cases where it might be more ambiguous if the leaving group were something else? I can't think of any. Certainly not in chapters 7 and 8. Others? All right. So we said that this reaction was bimolecular because the rate expression depends here because there's only one step, because both molecules are involved in the rate determining step. The rate depends on both. The reaction is first order in methyl iodide. We said that it is first order in Cn-, second order overall, because there are two concentration terms in the rate law, and so we'll call this an SN2 reaction. All right, so that's a summary of sort of our discussion last time. And if you recall, we mentioned that this mechanism, we observed data that is consistent with the SN2 mechanism for these starting materials, that is Cn- and methyl iodide. And yeah, Preston at home, we call them first order in each concentration because they only involve one of each of those molecules. But because two molecules are involved in the transition state, it's second order overall. I suppose for completeness, we should have starting materials and products here, and then transition state here. This reaction proceeds through a single transition state to the products. Again, there's no correlation whatsoever between the number in the mechanism designation, SN2, and the number of steps, which here is 1. All right. So at the end of the last lecture, we talked about how what mechanism actually operates is going to depend on which pathway is lower in energy for a given set of molecules. A molecule is going to go through the lowest energy pathway available to it. And so whether the SN1 or the SN2 mechanism operates is going to depend on how high this transition state is for the SN2 reaction versus this transition state for the SN1 reaction. And so I want to illustrate this using an energy diagram, but it's going to be souped up a little bit because we're going to do it in 3 dimensions instead of 2. And this is going to push on my drawing skills, and so I'll ask you to be tolerant of my poor drawing abilities. To help out with our discussion, I'm going to copy these 3 mechanistic hypotheses back down again. We'll shrink them to make it a little bit easier. Our 3 sort of choices for this reaction. And I'm going to make a 3-dimensional energy diagram. We're going to consider energy to be on, I guess, the z-axis. And maybe you want to use thinner lines for this. All right, so energy is here. On one of the horizontal axes, not sure whether it's y or z, we're going to put formation of the carbon-carbon sigma bond. So as we travel horizontally from left to right, we go from 0% forming of the carbon-carbon sigma bond to, we'll say, 100% forming, all right? And then along the other horizontal axis, maybe we have to have it angled out in this direction. We're going to put breaking of the carbon iodide sigma bond, and it's going to be 100% broken here. All right? So without even worrying about energy, let's consider the 3 pathways that we have available to us. I'm going to use orange for the yuck pathway, the one that we don't like. And I'm just going to draw an arrow from our starting position where before the reaction even happens at all, without worrying about energy. If I want to make the carbon-carbon sigma bond first, where should I draw my arrow? In what direction? And along what axis? Just left to right here, right? That would be, I make the bond first. This would be that weird and crazy intermediate that we proposed earlier where you have 5 things attached to carbon with a negative charge on carbon. And then if we wanted to show afterwards the carbon iodide bond breaking, which way would I draw my arrow from there? Sort of, well, trying to be parallel, kitty-cornered like that. So this would be maybe where our products are. Okay? And this would be a 2-step mechanism. We'd have a transition state from here to here and another from there to there. How about, and we said again, we didn't like that because we said this intermediate was too high in energy to be stable. What about option 2? If I want to break the carbon iodide bond first, where, starting again at my origin, where am I going to draw the line?
Along the axis.
So it should be along this axis that's coming out towards you. Break the bond first. And remember, at this stage, you're going to have the intermediate that is called a carbocation. This is the one where you've broken the carbon iodide bond completely. And then making the new carbon nucleophile bond should just involve going in that direction. This kind of illustrates an interesting point. Remember, thermodynamics don't care about mechanism. They care about starting point and ending point. So we've got two different, very different mechanistic hypotheses. They start at the same point. They end at the same point. We could not use energy differences that we might measure between starting materials and products would not tell us at all whether the reaction had proceeded through either of those pathways. And then our third and final option that we came up with, the one that actually operates here, is we do both at the same time. So what arrow should I draw there? Sort of just diagonal across, breaking the old bond as we form the new one. Okay. So those are three different pathways that we might, that start at our starting materials and end at our products. I told you that the orange one is outlandishly unlikely, so we're going to erase that and not worry about it anymore. Now we're going to try to see how energy varies as we traverse one pathway versus the other. So this is the weird part, because I'm going to try to draw this diagonal pathway, but in 3 dimensions instead of 2. I want to show you how energy varies as we go from 0% reacted to 100% reacted. So let's just imagine that on our energy axis, our starting materials are right at that point. And then products can still stay there. As products are lower in energy than starting materials, we already said that that was the case based on the strength of the bonds that we're forming. So for the SN2 reaction, remember what our transition state looks like, and remember that we only have one of them. And so that's going to be the high point of our journey from starting materials to products. And so I'm going to just paste it here so that we can remember it, and then I'll just shrink it down a little bit. So as we go from starting material to products for the SN2 reaction, we ought to go through a higher energy transition state. This is the part I'm sort of worried about, because I'm not sure I'm going to draw it that well. But oh well. We'll go from here, I didn't like that, here to there, and then down the slope all the way to products. And maybe I'll shade or use lines to convey that the curvy line above is right along that diagonal. Get the idea? Sort of okay? All right. So that's what we see if we go through the SN2 pathway. And maybe I'll make those, oh, no, also not. Bad, very bad. Okay, good enough. So now let's talk about what the alternative SN1 pathway might look like. We've got to get from our starting material to a carbocationic intermediate. And we said last time that that carbocation intermediate needs to be higher in energy than the starting material because we've broken a bond. So I'm going to sort of count up along this line and maybe put that carbocation right here. And then that carbocation has to, well, as we approach that carbocation, we have to go through a high energy transition state that is going to be the rate determining step of our reaction. At this stage, I can see that I should have given myself a little bit more space to begin with, so hopefully that's okay. While we're at it, I'm going to copy down the structure of that transition state that leads to the carbocation. This is the one where the carbon iodide bond is breaking, but nothing else is happening. Probably, and I'm going to use purple for this, so high energy transition state, ending with that intermediate. And maybe we'll use the lines again to show you where that peak is. And then this is the tough one because I'm going to need to draw out in front. By the way, Sierra at home is asking, what does SM stand for? Starting materials. Sorry about that. Once we get to that carbocationic intermediate, which maybe I will draw here again just to remind us, then forming the new carbon-carbon bond should involve another transition state sort of in this direction. And you have to imagine that purple line as being in the front. Okay? So this sort of represents the energy landscape that this molecule, methyl iodide, and then Cn- have to choose from. Now, whether it goes through SN1 versus SN2, the purple path versus the blue path, is going to depend on the relative heights of these barriers. The transition state here in blue, the SN2 transition state, versus the SN1 transition state in purple. So you could ask, well, in this case that we've talked about, why does the mechanism go through SN2? Because that is the lowest energy pathway presented. It's much easier to go through this lower energy transition state than to go through the higher energy one that leads to the carbocation intermediate. Okay? So two different pathways that a molecule can take, and it will take the pathway that's lower in energy. That's kind of an important picture, an important idea to have, because that'll help this whole thing seem a lot less arbitrary. How do I know when a reaction will proceed through an SN2 mechanism versus an SN1 mechanism? And the answer is you're going to have to get a sense for the relative heights of these two barriers, the SN2 transition state versus the SN1 transition state. So we're going to talk about things that make one of those more favorable than the other, and there'll be some fairly straightforward principles that we'll use for that. Before we do that, questions. What questions or concerns do you have?
Here's a question in the chat.
Oh, yeah. Does every molecule take the lower energy pathway every time? Good question. The answer is actually that these energy wells, I mean, this is a complicated answer. The energy wells on this energy landscape are populated with various energy levels. The more kinetic energy you have in a system, the more likely it is that you can spill over multiple barriers. So we're going to see later on in the course, and you'll definitely see it in 352. Sometimes to prevent multiple reaction pathways from happening, we'll lower the temperature so we don't have enough kinetic energy to get over both barriers, just the lower one. All right, others? So let's talk about some things that can change the barrier height here of this SN2 transition state. And you might expect for SN2, the rate of the reaction depends on not only the structure of the alkyl halide, but also on the nucleophile that you're using. So the barrier height for transitions, for the blue transition state, increases as we go from methyl to primary to secondary to tertiary alkyl halides. What do I mean by an alkyl halide? Well, the methyl halide that we're using as our starting material, the methyl iodide, is an example of an alkyl halide. Good enough. So let me show you why this is the case. For the methyl halide, remember that we said for SN2, the pathway happens with backside attack. When you've only got hydrogen attached to the carbon that the nucleophile is going to attack, it's very easy for the nucleophile to reach that carbon, dump electrons into the sigma star, and break the bond to give you the substitution products. As you successively replace each of those hydrogens with something that is not hydrogen, it gets increasingly harder for the nucleophile to reach the carbon that has the iodide on it. So up top we have the methyl iodide. I'm going to replace a one of those protons with a CH3 group. Now this is a bigger thing that starts to inhibit the nucleophile reaching the reactive carbon. And as we continue on, replacing some of those hydrogens with larger non-hydrogen things, it gets successively worse. So I'm going to continue to draw methyl groups that are replacements for these hydrogens and attempt to show you that the methyl groups get eventually large enough so as to cut off access of the nucleophile, and to prevent the nucleophile from attacking the carbon that is connected to the iodide. So by the time we get to the tertiary carbon, these methyl groups together are large enough so as to prevent the nucleophile from attacking. So we will see that if we measure the rate of the SN2 reaction as a function of the carbon that has the iodide, SN2 is fastest for the methyl iodide. It's still fast for the primary. It's a little bit slower for the secondary, and it's dead for the tertiary alkyl halide. What we mean is that as we change the structure of our starting material from being methyl to primary to secondary to tertiary, we are increasing the energy of this transition state to the point where we no longer are able to surmount that obstacle, and we can shut down SN2 reactivity completely just by having these alkyl groups in the way. Questions? If you want to see an example or see why that's the case, we can look at a methyl halide in the Spartan program, and we can see where the LUMO is. And the LUMO is on carbon. To our left is the carbon. You can see the carbon-hydrogen bonds poking out there. The blue lobe is the backside lobe of the LUMO. That's where the nucleophile would need to attack. And if we look at a space-filling molecule or space-filling model, we can see that the carbon that you need to attack is right there and easily accessible for a nucleophile. In contrast, if we just put, don't want to do that. We just put methyl groups on that halide. There's our new molecule. If we look at the space-filling view, now the carbon that you wanted to attack, you can hardly even see because of the adjacent methyl groups. It's that little triangle that's there, mostly occluded by those adjacent methyl groups. And if you want to see where the LUMO is, it's in the same spot, only the adjacent methyl groups are getting in the way. The blue lobe on the carbon is where the nucleophile would need to attack. Some of you may be concerned, what are those little red dots out on those adjacent hydrogens? Stay tuned. That's because of hyperconjugation, but we won't need to worry about that today. The point is that for tertiary alkyl halides, the carbons, the adjacent carbons completely block access to that LUMO, and that shuts down SN2. All right. So that's one of the things we can do to change the relative heights of these transition states. Go ahead.
There's a question in the chat.
Yeah, so if the kinetic energy was high enough, could it still reach the carbon? That's a great question, and I think the answer is probably, but for our purposes in this class, we'll assume that there is no SN2 at tertiary carbons. So we can consider that as absolute and immutable. If someday you go in the lab and you do an SN2 reaction and it works at a tertiary carbon, you can be surprised, and then you can come tell me about it and tell me why I was wrong, and I will congratulate you on your excellent skills. After I ask you to make sure the data actually say what you think they do. But go ahead.
From chapter 4, I think, that's an example of steric hindrance?
Yeah. So the question here in class is this an example of steric hindrance? And that's absolutely right. It's just electron-electron repulsion. As the nucleophile approaches, the methyl groups get in the way and repel it. Okay, good. Others, did I miss anything? Okay, one other strategy you can take to accelerate the SN2 reaction has to do with not the height of the barrier, but actually the height in energy of the starting materials. So you might reflect on the fact that in an energy diagram, there's two ways to make the activation energy. Let me just draw the activation energy. It's that energy difference there. There's two ways to lower that activation energy. One would be to lower the height of the transition state. The other might be to increase the height or energy of the starting materials. And so one way that you can accelerate SN2 is by using good nucleophiles. Good nucleophiles would raise the energy of the starting material and decrease the amount of distance you've got before you can go over that barrier. So this allows us to ask the question, what makes a good nucleophile? And fortunately, what makes a good nucleophile good is related to pKa information. So in general, good nucleophiles are conjugate bases of acids with pKa's that are greater than 0. Generally, these things have lone pairs as the HOMO, and often they are negatively charged. So I'm going to just list some that qualify as good nucleophiles based solely on their pKa's of their conjugate acids. So the acetate anion, its conjugate acid is acetic acid, and its pKa is 4. So that qualifies, and we will often see acetic acid act as a nucleophile. A negatively charged sulfur, that's called a thiolate, is the conjugate base of a thiol, and that has a pKa of 8. Cn minus that we saw in this example is the conjugate base of HCN, which has a pKa of around 9. Similarly, there's a molecule, an anion called azide, which has this kind of strange structure. We often abbreviate it as N3 minus. Its conjugate acid is HN3, which also has a pKa of 9. And we could continue. Ammonia, conjugate acid is the ammonium NH4 plus ion, also has a pKa of 9. A primary amine, the conjugate acid is this primary ammonium, pKa of 11. And, you know, we could include on our list things like hydroxide or alkoxides of various kinds. Their conjugate acids are water and alcohols, pKa of 16. One of the strongest nucleophiles we will encounter will be the conjugate base of an alkyne, which has a pKa of 25. So these are all molecules that you can think of as being good nucleophiles. Just as an aside, bad or weak nucleophiles would include water and alcohols whose pKa's are, who have conjugate acids, hydronium and oxonium ions with pKa's of around -2. So you'll need to work on that, sort of remembering the range of molecules that can be good nucleophiles. And your cutoff point is where their conjugate acid has a pKa of around 0. Okay? Yes?
Are all of the nucleophiles about like equally good, or is it like the one with 25 is better than the one?
It's a good question. Are all the nucleophiles equally good, or do they get better? Yeah, they do get better the more, the less stable the conjugate base is, or the weaker the acid, then yeah, the more reactive the nucleophile is. So just as an aside, there's going to be a problem in the future, a challenge in the future, because as we increase the reactivity of these nucleophiles, they become better and better, not only at attacking carbon, but also at removing protons from things. And we'll need to start to worry about that as we get to sort of hydroxide and alkoxides. Beyond this point, it becomes difficult for a nucleophile to selectively attack carbon versus a proton. That may not make a lot of sense now, but we'll hopefully clarify that as we start talking about elimination reactions. And then yes, Preston, they are good nucleophiles because their conjugate acids are relatively weak. Other questions? So if we want to promote the SN2 reaction, we can either change the structure of our alkyl halide to be as unsterically hindered as possible, or we can use more reactive nucleophiles. Interestingly, using more reactive nucleophiles doesn't help us if we want to go through SN1, because the nucleophile isn't even involved in that first step with SN1. In fact, if you use a good nucleophile, you may bias the system toward SN2 by making it easier to go in that direction. All right, so we want to now talk about ways that you can, well, actually, before we do that, I want to issue a warning, and that is that we're going to see as we talk more about Chapter 8 that there is another thing that can happen to these starting materials. It sort of goes off in another dimension, which we won't even attempt to draw on this same diagram, because who's ever, well, you show me how to draw a third dimension, a third horizontal dimension, and then we'll go from there, right? And there's also another direction we can branch off from this carbocation point. For right now, store in the back of your mind that a molecule that is a good base has something else it can do, starting from this starting material or from this carbocation. Don't worry about it too much, other than make a place in your mind where you're going to file that away. Now, if we wanted to accelerate the SN1 reaction, what would we do? We would need to think about lowering the energy of this transition state, the purple transition state 1, and or the energy of the carbocationic intermediate. And we're going to see that the energies of the carbocationic intermediate and the transition state are tied together quite closely. We will see that the transition state, if we zoom in on it, and we compare that transition state to the carbocationic intermediate, the transition state is actually pretty close in structure to a carbocation. In the transition state, the iodide leaving group has already mostly left. There's a buildup of partial positive charge on the carbon. So we're going to see that the same things that make carbocations more stable will also make transition state 1 more stable. What I mean is that the transition state and the intermediate resemble each other closely in structure, and so what's good for one is good for the other. If we can find things that bring the transition state down in energy, it will also bring the carbocationic intermediate down in energy. So, how could we make a carbocation and the transition state that leads to it lower in energy? To talk about this, we need to learn something about carbocation stability. And interestingly, the trend for carbocation stability is exactly the opposite of the trend for steric hindrance in SN2 reactions. So we will find that tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than methyl carbocations. What do I mean by a tertiary carbocation? I mean an sp3 or sp2 hybridized carbon surrounded by 3 alkyl groups versus 2 alkyl groups versus 1 versus none for the methyl carbocation. All right. So that's probably enough of a place to stop now. That's basically where we got to last hour. I want you to be thinking about why a tertiary carbocation is more stable than a methyl carbocation. I will give you a preview on the answer. It's called hyperconjugation. And think about it and see if you can figure it out. We'll talk to you again on Wednesday.